Alright, so this is your first of 3 videos that are going to look at complex numbers as vectors. We're also going to look at complex numbers as polar coordinates, alright? So the first thing we want to do is review Argand diagrams. And so let's go ahead and draw an Argand diagram. And you may remember that that's just a Cartesian plane for which the x is the real and the y is the imaginary. Alright, and so what we're going to do is let's just practice a couple of them just to make sure that we remember. So let's say that z equals 3. And so 3 is all real, and so that point would just be on the real axis right there. Oops. Right there. Doop. So there we go. Let's try another one. Let's try z, and we'll just label this one as 2. And let's try z2 equals 4 plus 3i. Alright, so we're going to go to 4 on the real, and then we'll go up to 3, positive 3 on the imaginary. So 4, 3, right there. And so that right there would be a point in the, for z2. Alright? Now, these each could be represented by vectors, of course. You can start at the origin there, and this is then representing a position vector of those points in the imaginary plane, in the Argand diagram. And so then what we're going to do is we're going to go ahead and let's do one more. Let's do z3, and we'll just go negative 3 minus I. And so just for good measure, we'll go down to negative 3 and then negative 1 for the imaginary. And so there's your reminder of your Argand diagram. Now what we're going to do is we're going to go ahead and look at a couple of different things. Okay, let's see what it would look like if we do, let's go negative z2. Alright, now vectors are going to be the same. So if we take z2 and I make both those negative, then that will be negative 4 plus 3i. Sorry, not plus 3i, minus 3i. And so if I do that, then that will be at negative 4 on the real, and then negative 3 on the imaginary. And you'll notice that that is exactly the same thing as the z2, except now it's going in the opposite direction. So we're starting to see a little bit how this is following the same properties as vectors. Alright, how about, do you remember this one? The conjugate. Now hopefully you remember that the conjugate means that the whole number stays the same and the imaginary number is the opposite. Now this is because that way when we multiply them together, you know, a conjugate times its original, when you multiply the conjugates, the imaginary part goes away and we get a real answer. So if we graph this one, 4 minus 3i, we go 4 in the real and then down 3 in the imaginary. And so there we go, it's right there. Which you'll notice then that z2 conjugate is reflected in the x-axis of our original z2, right? And that negative z2 is a y-axis reflection of the conjugate, or a rotation around the origin. Alright, so these are just some basic properties that we want to recognize and start to see that these things are just vectors that are getting moved around and changed and looking in different directions. Alright?
Alright, so now knowing that we can write these complex numbers as vectors, that then allows us to do some mathematics with them. So let's take a couple of examples. Let's take z2 and z3 here, and we're going to go z2 plus z3. Now if we think of these as the components, which is exactly what they are if you look at our Argand diagram, then all we need to do is we can add the x components, which is everything in the real direction. So I go 4 plus negative 3. So this essentially is 4 plus 3i plus negative 3 minus, negative 3 minus I. And so essentially we put the x components together, which is 1. And I put the y components together, or the imaginary components, which is 3 minus 1. So that would be plus 2i. And therefore I get the result. Now I could show this geometrically, of course. All I would need to do is first take z2, which was the red one, and then I would go head to tail. And so that would be down 3 in the real direction and 1 right there. So there we go. Note that that vector is the same as this one, it's just with a different starting point. And our final result is a real of 1 and a imaginary of 2, which is exactly what we have there. So we can show these things both visually, graphically, and algebraically.
So now what we're going to do is we're going to go ahead, and obviously you can do the same thing. We could do this with, put coefficients there, right? We could go 2 times z2 and minus z1. Now this is just going to be the same thing. You just treat this as 2 times 4 plus 3i, and then we subtract the z1, which was 3 there. Alright, and then we just distribute. We got 8 plus 6i minus 3, and then we get 5 plus 6i. And so you could do the same thing just by taking vector 2 and doubling it, and then subtracting 3 from the real, and hopefully that would then give you the 6i plus 5. Alright, so we got a basic idea now of what's going on, and I just want to remind you of a couple other things before we go on to the next video, alright? So one of these things is to remind you of the modulus. The modulus, remember, is the length of the vector. So let's deal with maybe the length of z2. Now this makes sense if we're looking at our Argand diagram here, right? So if we're doing z2, remember z2 was this first red one right here, which is 4 in this direction and 3 in the I direction. And so to get z2, the length of z2, we just go the real part squared plus the imaginary part squared, and then we square root all of that, right? Because all we're doing is a squared plus b squared equals c squared. And so z2 I can get very easily by doing the square root of the real part, which is 4, plus the imaginary part, and don't worry about the I, just how many units it is. It's 3, so 3 squared. So 4 squared and 3 squared is 16 plus 9, which is 25. Ooh, that worked out really nice. And so the length of z2, or the modulus, is 5. Alright, so that's pretty much all we got right there. Alright, now we're going to talk a little bit more about these, but this, of course, this idea of using the modulus with imaginary numbers could also be applied to finding the midpoint of a segment, to finding the distance between 2 points, right? If I had 2 different points, if I wanted to find the distance between z2 and z3, then we just find the difference of the x values and the difference of the y values, and that's what goes here instead. All right? And so obviously these ideas can all be expanded in that way. All right? Everything that you could do with points on a Cartesian plane, you can now do with points on a complex plane. The only thing is that we're going to ignore the I part because that's just your y value, and we're going to use that as our second value, as our y value. All right? So hopefully that gives you a little bit of introduction. And tonight you're going to be looking at several different properties of moduli, and by using these things it's going to help you kind of get through that, recognizing these patterns of the reflections and all that kind of stuff. So hopefully that'll be something that will be interesting as you start to deal with the modulus. Okay? Alright, that's the end of the first video.